Hey, it's Tony from Adafruit, and in this video we're going to look at how to use a TFT or an LCD display with MicroPython. So I'll show a quick example of a little small display. So this is an example of a TFT or an LCD display. So really similar to what you're probably looking at right now, like a computer monitor, little LCD display. But this is nice in that these are tiny little displays that you can connect a MicroPython board to and start controlling and drawing on with MicroPython code. So we'll dive in and see how to use this. And this specifically is for the ILI9341, or it should work with the ILI9340 display. So it's just a certain type of TFT driver chip that I'll show you a little bit more about. And it's pretty common. We have a few breakouts and this nice little FeatherWing in the store that you can look at. So let's just kind of dive in and we'll get started with how to use this with MicroPython. So we'll go to the main desktop display here. And hopefully the audio is coming in pretty well. I didn't monitor this before, so let me just do a quick on-the-fly adjustment because I had changed my audio preferences, and so now we can see how the sausage is made here. Okay, yeah, so my gain is let's crank it up to 100. So okay, I think that's a little better. Hopefully the audio is coming in fine. We'll see in post if I have to boost this up later. So anyways, though, so what you see here, I have this is the TFT FeatherWing. And I'll show you on the back. It's called a FeatherWing because it's a little bigger than most FeatherWings, but of course on the front you have this nice little display. This is 2.4 inches if I remember correctly, and then on the back here is where you plug in the feather. It actually has a little micro SD card slot, an on-off switch, and a reset button right here. And this is the ESP8266 FeatherWing, and so this is, or Feather rather. So this is using the ESP8266 processor, running MicroPython, of course. And so we'll look at this in a second. And the nice thing about the Feather and the FeatherWing is that it just slides right into it. Oops, let me get the pins lined up the correct way. So look at that, it's connected. It's pretty simple and easy to connect the Feather to the FeatherWing like that. And so let's take a look then at what this display is and what we're going to look at. So this is the new guide in the learning system that I created. This is the ILI9341 TFT and FeatherWing guide. And so I'll put a link in the description when this goes up on YouTube so you can take a look at that and follow along at home. And basically this shows how to use this ILI9341 display with MicroPython. So there's a little MicroPython module that we'll look at, and it'll show you the basics of how you can draw pixels, you can draw a filled rectangle, and that's kind of the limit, or you can clear the whole screen. So there's not too much that you can do beyond pixel drawing right now, but I'll show you a little hint of something I've been working on that hopefully tomorrow I'll do a little video or a guide on to show basic drawing of like lines and squares and circles and triangles. I basically ported the GFX, the graphics library from Arduino, to MicroPython, and it's a little bit slow because it's all pure Python, and so it's kind of showing maybe what kind of performance you can expect from Python code. But in the future maybe we'll do some optimized versions. But for now, in this video, I'm just going to show you how to set up, how to initialize this display, and just get to the basic pixel drawing commands after that. So let's just dive in. Hardware wise, it's pretty straightforward. You just need a MicroPython board. I did make a note, it doesn't currently work with the SAMD21 MicroPython port. There's some kind of issue with the SPI connection that we'll have to troubleshoot and figure out, hey, it's a beta port, not everything works yet, but it does work really well with the ESP8266 port that I was just trying it with for this example. Obviously you need an ILI9341 or 9340 display, and like I mentioned, the TFT FeatherWing, and I'll put a link to it. This is the product right here. Really easy. If you have a Feather, this is a great way to use this display. So it has a little 2.4 inch display. Also of note, this is a touch screen. There's actually a resistive touch screen on here, but the module in the library doesn't have support for the touch screen yet, so you can't use the touch screen in MicroPython just yet. In the future, we'll have to do a driver for that and allow you to read the touches and things like that. That'll be pretty cool once you have that functionality. Okay, so, or you can use a breakout board. So there's like a 2.8 inch breakout. That's a little bit larger display. There's a 2.2 inch breakout and a 2.4 inch breakout. And it's a breakout board just because it's something that you'll need to connect to like a breadboard like this. And it exposes a lot of different connections. These drivers actually can be used in a parallel 8-bit mode or a SPI serial mode. And this driver and this module only uses the SPI serial mode for these boards. So if you have the breakout, you have to use the SPI mode for this. And the FeatherWing is just built to use the SPI connection. for this. Okay, so to connect this, like I just showed with the feather and the FeatherWing, just slide the feather right into it. Super easy, and it'll automatically use the right SPI connections. Make sure that you flip the switch on the bottom into the on position. That might throw you off a little bit. It threw me off for a second that you plug this in, and why isn't the board working? Oh, because there's an on-off switch here, so make sure to turn that on. And if you're using the breakout board, again, you just have to wire it up using a typical SPI connection. So the SPI clock from your board to the breakout, the MOSI or master output slave input line has to be connected from your board to the breakout board. You don't actually have to connect the MISO, basically the master input slave output. So the MISO is kind of the data output from the board or from the display to the board, and it's not being used in this case. So it's, you can ignore it. You can just leave it off completely. You do need two GPIO lines. You need one for the chip select and one for the DC or the data command byte line. And then you could optionally also connect the reset line to one of your GPIO lines. I don't show the connection here. There's auto reset logic, so you don't have to use the reset line, but it's there. You can use it if you want. There are other lines too. You can control the backlight on the breakout, and even on the TFT FeatherWing, it's connected to a GPIO line, so you can turn that on or off. I don't show examples of it, but it's just like toggling a GPIO line to control that. And then one really important thing, if you're using the breakout, it needs to be told to go into the SPI interface mode. And there are a couple ways to do it. You can solder closed some bridges on the back that will permanently put it into a SPI mode. Or you can just temporarily connect the IM3, IM2, and IM1, but not IM0. So there are 4 of these, IM3 through IM0. 3, 2, and 1 are what you want to connect to 3.3 volt power. So not 5 volt, 3.3 volt power. That just tells the board, go into SPI mode, because by default it goes into this 8-bit parallel mode, which you actually have to use the other side of the breakout to access. And we don't have code for in MicroPython anyways, so you're not going to be using that right now. But it is actually potentially a little bit faster. So if someone wants to take a stab at it, you might be able to get quicker update rates, because you'll see that this display, you're limited to how fast you can push data over that SPI connection. And I'll show you a little bit like where that matters. So if your SPI bus is not running at a high speed, you will see pretty slow pixel updates. And even at the current speed, it's still relatively slow to update the display, because all of this logic's being done in Python, and so it's interpreted code. It's not super fast C code yet, so don't expect to be doing like super fast video and animations and things like that. Again, that's probably a case where you want to look at maybe doing some optimized C routine that talks directly to this display potentially. But if you're just drawing like a basic little interface or something, this might be good enough to play around with and see how it works. So, okay, so that's the wiring and the setup. Like I said, I'm using the TFT FeatherWing and the ESP8266 Feather in this example. Let's dive into the software part. So for this, there is a little MicroPython Adafruit RGB display module, which is just a little library. I'll put a link in the description when this goes up on YouTube. There's actually a bunch of other displays that are supported in this library. So things like SSD 1351, that's like a color OLED if I remember correctly. The ST7735, that's like another TFT driver. So other chips are supported in here. I don't have examples of those, but you could check out like the documentation here and see how they work. But for now, I'm just using the ILI9341, which should also work with the 9340 if you have one of those chips, which is, I think some of the smaller displays use that one. But anyways, let's go back to the guide. And the first thing is, obviously, you need to be running MicroPython on your board. I'm using ESP8266. Make sure you're using version 1.8.5 or higher. And like I said, the SAMD21 port doesn't work right now. So at some point, we'll have to sort out that issue and get it working. But the next thing is you want to copy the ILI9341.mpi and the, oh, this is a small mistake, the RGB.mpy. Let's edit this page on the fly here. Look at this. We'll fix problems as we go. So let's see, so it's the RGB.mpy, and that is important because the .mpy files are smaller, they take up less memory. You could copy over the .py file, but it's going to have the full source code, which really isn't what you want. You want the precompiled or kind of bytecode compiled .mpy file. Anyways, though, you can find these under the releases tab of this library. And there's a link in the guide that shows this. So here all the .mpy files are. So you want to grab rgb.mpy and ILI9341.mpy. And I've downloaded those already. And then you want to copy them onto your board. And for the ESP8266, I'm going to use the AMPI tool. I have a link in the tutorial here if you haven't used that before, how to use it. It's just a tool that copies files onto MicroPython boards. So in my case, I actually already have set up this AMPI underscore port environment variable. So because I set this environment variable, I don't have to specify this every time I use AMPI. So I can actually just do AMPI ls. This is going to list all the files on my ESP8266. Oh, well, actually I have to connect the board first. That's maybe step one, is connect your MicroPython board to your computer. So let's do that. There we go. So I just connected it. You can see the LCD kind of turns on. It goes into like an initial white screen kind of state. Okay, so let's list the files, and now you can see. So on my board, I have this ILI9341.mpy and rgb.mpy. I'll just show you if you want to load those files up. You can use the AMPI put command, and it's in my downloads directory. I have my rgb.mpy, so I can just put this file onto the board, and it takes it a second. And then I can also put the ILI9341.mpy, and I'll put that on the board. The gfx.mpy, you don't need this. I'll show you at the end a little hint of something I'm working on, the graphics library basically. So I've already got this on my board, but you don't have to have this to use the display. Okay, so I copied the files over, and the next thing is we need to initialize the SPI bus. And so first connect to the REPL, the serial REPL, and you can use the web REPL, you could use whatever for this, but I'm just going to use the serial REPL. So I'll use the screen command and connect to that Scilab's USB to UART device that's on the ESP8266 board I'm using, 115200 baud, and I've got the Python REPL, the Python prompt effectively here. So the first thing is to initialize SPI, and this is specific to the ESP8266. So on the ESP8266, you want, and with the Feather and the FeatherWing like this, to use the hardware SPI connection, you want to initialize it like this. So create a SPI object and an instance of the machine.spy class. And then it's super important that you need to pass this very cryptic 1 as the very first value here. And so this is telling the ESP8266 MicroPython port to use its hardware SPI interface. If you leave this out, it will actually work, but it will use a software SPI interface. And I'll show you maybe after this what the difference is. But you really want to use hardware SPI because that's going to be much faster than the software SPI interface. Software SPI is basically just bit banging. It's implementing the clock and the data output and the data input lines just using any GPIO lines. So it's only as fast as the ESP8266 CPU can run, which is kind of limited. I think it's only like 84 megahertz, but you're not going to toggle GPIO lines at 84 megahertz. You're going to toggle at a much slower speed. And so, by using software SPI, you lose a bunch of speed versus hardware SPI. There's some digital logic inside the chip that actually implements the whole SPI protocol. So it's a lot faster. It can run at higher speeds. And the speed is important. So baud rate is a parameter you specify. This is the speed of the SPI connection. And these displays can actually run up to about like 60 megahertz or so from what I saw in our Raspberry Pi Python library. Now I tried that on the ESP8266, and it doesn't seem to allow you to create a hardware SPI connection at 60 or 64 megahertz, but it does work with 32 megahertz, so 32,000,000, so 32 million basically. This is the speed in hertz of your SPI connection. And so that's what I'm going to do. I'll use 32 megahertz for this, so it's pretty fast. That's a quick connection. But remember, so this display is 320 by 240 pixels. Each of those pixels is 18 bits of color, if I remember correctly. That's a lot of data when you want to push out an entire frame of your display. And so that 32 megahertz rate might sound really fast, but when you're pushing millions of bits, it's still not that quick. So, you can actually see the entire screen refresh even at a high rate like this. Okay, so that's how you initialize the hardware SPI connection. Now to initialize the display, you import the ILI9341 module, and then you create an instance of a display object. From inside of that module, there is an ILI9341 class you create an instance of, and this needs to take in the SPI interface that you created before, and then it has to take in at least the chip select, the CS line, and this should be a digital input, so machine.pin. And on the TFT FeatherWing and the ESP8266 Feather, the chip select line is digital input 0. You can find this on the TFT FeatherWing guide, and I have a link in the MicroPython guide here that kind of tells you where to figure this out. So if you go to this link right here, it'll tell you for each of the chips. It's different on the SAMD21 breakout. If I remember correctly, it's like digital input 9 and 10, I think, are the chip select and DC lines, versus the ESP8266, it's digital input 0 and 15 are those lines. And then if you've wired this up to a breakout board, then you need to look and see which one you connected it to. So in this tutorial, I show 0 and 15, but you know, you might have wired it up differently. You can use any GPIO lines. Just make sure on the ESP8266 that they don't have like a pull up or a pull down connected to them, because some of the lines do, and sometimes that matters. So you have to be a little careful with this. Okay, and then you also have to specify the DC, or the data command byte line, and that's machine.pin 15 with the TFT FeatherWing and the ESP8266. And that's it. There is also an optional reset or RST line. If you have that connected, you can specify that as a machine.pin. I don't have it connected. It's not connected on the TFT FeatherWing, so ignore it. Don't worry about it. And I think I do mention, oh yeah, by default, it's going to, oops, as I move this thing around, it's going to specify your width as 240 pixels wide, which sounds a little weird, but basically the default orientation of this display is like this, where the origin is in the upper left-hand corner here, and then you have 240 pixels across in the X dimension and 320 down in the Y dimension like this. And you can override that. You can tell it you might have a different width and height display, although I think all of these ILI9340 displays are 240 by 320, but I might not be totally sure on that one. But if you need to override that default, you can specify those as other keyword parameters to this initializer. So, okay, oh funny, as I move this, I must have reset the board on accident there. So I need to go through and retype in these commands here. So spy equals machine.spy1 baud rate equals 32 megahertz, and then we'll import our ILI9341 and create an instance of our display again, ILI9341.ILI9341, and the spy, and then chip select equals machine.pin 0, and the data command equals machine.pin 15. Okay, here we go. Now I hit enter, and okay, this is good. So the display, it just cleared to black. And you might see some flickering. I think that's just because my camera has a refresh rate that's kind of similar to probably the refresh rate of this LCD. So this, you don't actually see this flickering when you're looking at this in real life. Okay, so now at this point we're ready to draw on the display. And it just has, like I said, basic pixel commands right now, but look forward to some libraries in the future that should add things like line drawing and circle drawing. And I'll give a little hint at the end of this video of something I'm working on. You can fill the display with a color. And the interesting thing is to generate a color, you actually have to call a function that's in this ILI9341 module. So the display.fill command will fill all of the pixels on the display with a single color. And I want to call the ILI9341 module .color565 function. And so this function takes in your red, green, blue color component values, and these are bytes, so a value from 0 to 255. So if I want like a bright red color, that'll be 255 for red, that's full intensity of red, 0 for green, and 0 for blue, so no blue, no green color. And so this function is just going to return back a byte that has this 18-bit color value encoded inside of it. So it's just a little helper function. Like you could pre-generate this value and instead of calling this function, just pass in that 18-bit value to the fill function if you want. But in most cases, you probably want to convert your red, green, blue color into something you can fill on your display. Okay, let's hit enter. And hey, look at that. You see the whole display just updated. But notice, you know, it wasn't like super fast. You could actually see the update happen there. And some of that is the speed of that SPY connection. So again, you know, it's got to push out every single pixel over that SPY interface. And some of that is also just the overhead of this running in MicroPython. So the code for this is in effectively pure Python code. So it's just sending out the SPY commands to set all these pixels and things like that. So it's, you know, you do kind of start to see some of the limits of how fast things can run. If you just want to clear the display to 0, like put it back to a black color, just fill with the value 0. And so that's going to give you a black color, like nothing on the display effectively like that. So, okay, so that's how you fill, how you set all the pixels on the display. And maybe just for fun, I'll show you what happens if you don't use the hardware SPI interface. So I'll press Control D, D as in dog. That's gonna do a soft reset of the board. So you see it just did a soft reset. So now the whole board is like reinitialized, and I have to basically start over and reload things from scratch. Although interesting, the web REPL is running and it looks like it ran out of memory. So I'm actually just gonna, let's disconnect and reconnect the board just to do a hard reset instead of a soft one there. So okay, so let's reconnect. Now I wanna show the difference. I'm gonna reinitialize the SPI interface, but I'm going to omit, I'm not going to include that magic 1 parameter. I'm just going to say baud rate equals 32 megahertz. And we're not going to get that baud rate. You know, it works, the function returns, it doesn't throw an error, but you're not getting that speed, and you'll see in a second why not. ILI9341, all right, let's import that module. Let's create our display again, and let's give it that SPI interface, and then the chip select line, which is pin 0, and the data command line, which is pin 15. And okay, that seems okay. Everything is working so far. Now let's try to fill the display with the red color again. So let's do ILI9341.color565 with a full red, or actually how about, let's do a blue color, or a green color rather, just to show a different color. Okay, so now let's do this, and oh boy, that is not as fast as what you saw before. This is going to take like 10 seconds or so to fill this entire display up. Even longer than that probably. So before, you know, if you go back to the video, it took maybe, I don't know, a second at most to fill it red. And that was a good 5 or 6 seconds. So what happened here is, because I didn't have that magic 1 parameter in front of the SPI creation here, it defaulted to use a software SPI implementation, so a bit-banged SPI implementation, which just happens to use the same pins as are connected on the TFT FeatherWing and the ESP8266. So functionally it works. It's just instead of the ESP8266 hardware driving the SPI interface, it's actually code running on the CPU that's toggling the lines high and low manually. So you see the speed difference. It's an order of magnitude of speed difference. Like, you know, what was 1 second took like 10 seconds or so for that. So just word of the wise, if you see things are really slow, you probably want to, you know, reset the board, and then let's import machine again and make that SPI connection. So give that magic 1 parameter, and then baud rate equals 32 million. Let's make sure I got that correct. Yeah, 32 million. And then import our display again, 9341, and create our display. Display equals ILI module .ili9341 and SPI, and then chip select. Hopefully this is the last time I have to type this out. And then the data command line equals machine.pin15. Okay, and then let's display.fill 0. And there we go. So you see, a lot faster to fill that time because it's using that hardware SPI interface. Okay, so beyond filling, you can also set pixels. So there's a pixel function. This takes the X and the Y position of the pixel. So like pixel 0, 0, and then it takes a color. And again, you can use that ILI9341 module.color565 function. And let's make this a white pixel. So 255, 255, 255. That's basically red, green, blue at full intensity, which mixes together to make a white color. And so if I set this, then you might be able to tell there's a tiny little white dot right here in the upper left-hand corner. And then let's go all the way to the bottom, like the opposite corner. So again, remember 240 pixels across, which means 219 is the last column because it's zero-based index. And then 320 down, or no, sorry, 240 means 239. And then 319 down is the bottom row basically for this. So let's do that. And there's a tiny little white dot right down there that you can see. And then if we want to go in the middle, we could pick a pixel that's, you know, somewhere around like 120 and 160. And so we should see that, yeah, right in the center is a tiny little white pixel there. So that's the basics. You know, you can put a pixel and you can clear the display. There is also a filled rectangle function. So display.fill rect, I think it's rectangle, if I remember correctly. And actually, let's just go back to the guide to make sure that I have this correct. Yeah, fill rectangle. And this takes in the X and the Y position. So let's put this one at like 10, 10. So offset from the origin by a little bit. And then it takes a width and a height in pixels. So let's say 100 pixels by 100 pixels. Let's make a square. And then a color again. So we'll call that color 565. And let's make this a pink color. So blue and red at full intensity. So I do that. And check that out real fast. You know, there is, boom, a nice square that's displayed there. So that's cool. I mean, that's good enough to make a Pong game, you know, a Pong clone. You could have a paddle at the bottom and the ball as a square and just have it bouncing around on here. And that's pretty fast. I mean, you know, that drew at a reasonable speed. Let's set that to like a red pixel. And you see, yeah, you know, that's, you can see it update. It doesn't happen instantly, but it's pretty quick to do that update here. So okay, cool. So that's all that you can do effectively right now with the pixel drawing in this module. So again, it's super basic, but it is enough to get started. And you can use this if you go back, and I'll put a link in the description below to the text drawing video that I did. I think that was the last video I did from Friday last week. That video, I show how to draw text on any pixel-based display using this little text bitmap font module that I made. And so you could use that with this. You just have to plug in the pixel drawing function to draw on this display, and you'll be able to draw text, like write a line of text using a 5 pixel wide by 8 pixel tall font. So, you know, it'll probably be a little bit small on this display, and I don't have any resizing implemented yet, but it is possible. You could draw some stuff on here. Okay, so the next thing I wanted to show, this is just a preview. This isn't in the guide, but there will be a new guide on this soon. I basically wanted to take a stab at porting the GFX library, which is the Arduino graphics drawing library that we use for all of our Arduino display modules and libraries. So this TFT FeatherWing you can use in Arduino, and you can use with any of the Arduino supported boards. So like the Feather M0, the Feather 32U4, connect that to this display, you can control it in Arduino, and you'll use this GFX library, which has basic line, rectangle, circle, triangle, you know, the primitive drawing commands are implemented there so that you can do things like draw a line or draw a triangle on here. And so I've been working on porting that over to run as a MicroPython module. And there are a couple ways that I could do this. So the fastest way would be to implement it in C as a new module that is compiled into your MicroPython firmware. And at some point we might end up doing that because you know, there are cases where you really want that fast speed. But another way to implement this is like I did with the font rendering module, I could implement it in Python and then just plug in the pixel drawing function. So I can write the code that knows how to draw a line or knows how to draw a rectangle or a triangle or circle even. And every time it needs to draw a pixel, it just calls some function that you provide. So if you're using this ILI display, you can provide its pixel drawing function. Or if you're using something like, you know, a NeoPixel grid, you can provide a pixel drawing function that lights up the appropriate NeoPixel. Or if you're using like the CharliePlex display, so this is a nice little 15:7 grid of LEDs. You could have lines and circles drawing against this by just plugging in the pixel drawing function for the CharliePlex display. So that's kind of my goal with it. And you know, it's not going to be as fast as a C implementation because it's Python code that's actually drawing the line. And so that has to be interpreted and run in MicroPython. But you know, for some cases, like if you're just powering this little 15:7 matrix, not a lot of pixels there anyways, so if you're drawing like a circle, it's not going to be this giant thing. So it might be fast enough. It could be good enough to give you some basic drawing commands with it. So I'll give a quick little preview of it. This is kind of the code for it that's a work in progress still, but it should be out there pretty soon in the next few days. And again, this is just like the bitmap font rendering library where you create an instance of this GFX class and you have to pass in the width and the height of your drawing area. This is just so it can optimize. If you try to draw a pixel outside of those bounds, it'll just ignore that and it won't spend time trying to compute how to draw lines and things across there, although it's not fully implemented yet, but eventually I'll have that in here. But the important thing is this pixel function. So you have to draw in like the comment, or you have to pass in a function that's going to be called every time this library needs to draw a pixel. So later on in the library, like further down below, you can see I have functions like a rectangle drawing function or a line drawing function. And this function has all the code to draw a line pixel by pixel. But then every time it needs to draw that pixel, it calls this pixel function that's saved on the class itself. And so that's what you pass in here, and that's how this can work with any display. So this can work with this TFT display, or it can work with the Charlieplex display, just depending on what pixel drawing function that you pass in here. So that it makes it nice and flexible, and that I write this code once and I use it against any display. But we'll see, you know, it's maybe not super fast. It is nice in that the code is really clear, so I'll show you what I implemented. And there are a few other optional parameters here. There's a horizontal line drawing function and a vertical line drawing function. These are nice in that if for your display you have a fast horizontal line drawing function or a fast vertical line drawing function, because for some of these displays like the ILI9341, depending on what the SPI protocol looks like, you might be able to draw a horizontal or vertical line very quickly by just sending a command that says, okay, you know, fill this buffer of your memory with this value. And if, you know, for a horizontal line, maybe that buffer of memory is all contiguous and it can just quickly blast out a line of data. So if you have a faster horizontal line or vertical line drawing function, you can send it into this class and it'll use those and hopefully speed things up a little bit. But if you don't have those, I actually just have a little naive implementation here where it's just loops through. You know, if I want to draw a horizontal line, I basically just start at the beginning and just pixel by pixel draw each of those pixels across. And same thing for vertical, it's just start at the top and then draw each of the pixels down in a loop here effectively. So, you know, you're just using the pixel function across a loop. So it's nice and it'll work, but you'll see it's going to be a little bit slow when it uses these. So the functions I've implemented, I'm basically copying the GFX library and kind of its naming. So there's a rectangle function which just draws a rectangle that's 1 pixel wide but with nothing filled inside of it. There's a filled rectangle, so you can draw like a filled in square, kind of like the filled rectangle function on the ILI library. But, you know, as you noticed, the ILI library is pretty fast, whereas this one we'll see is maybe a little bit slower right now. There's a line drawing function, super handy. So this will just draw from any point to any point a line. It can be up, down, it can be like at an angle or whatever. It's using what's called Bressingham's algorithm, which is a pretty well-known graphics algorithm for drawing a line that kind of minimizes the amount of math that you have to do. Like it just does, there's actually like no division at all. It's just doing integer addition effectively or subtraction for this. So very important way back in the day when computers were slow. Also important now when MicroPython and microcontrollers are a little bit slow. So these kind of algorithms are handy to have. There's a circle drawing algorithm, and I have to give credit to Phil Burgess, who created the GFX library, and I've just ported it over. So all of this code is Phil's magic. This is great stuff, and it was super easy to port. But the circle drawing, this just takes, the XY center of the circle and then the radius, and it will just draw a circle. And there's a filled circle, obviously, too. And then triangle, you can draw a triangle, you give it 3 points, it'll draw a single pixel wide triangle, and then there's a filled triangle. But there's a bug in here right now where I'm still kind of troubleshooting some things. It works, but I'll show you a case where it doesn't work. Okay, so let's actually look at an example here. I have this little ILI9341 test example that I've been kind of playing with here. So this is just showing, what the usage will look like for this graphics library once it's published. And I'm going to do a whole separate guide on this. So again, this is just a little preview of this. But I'll show you, I'm basically importing the GFX module, the machine module, and the ILI9341 display module. I'm setting up the SPI bus exactly how I showed before, 32 megahertz hardware SPI. I'm creating the display exactly as I showed before, using the same chip select and data command lines. I'm clearing the display, and then I'm creating an instance of this GFX class that we were just looking at right here with this code. And I'm passing in, it's a 240 pixel wide by 320 tall display. And then here's the magic where I'm passing in this display object, its pixel function. And so that's how this GFX class will know when it needs to draw a line, how to draw each of the pixels of that line. So it's going to use the display.pixel function. And then the way this works, so let's uncomment this. So I'm going to call the line function. And so this should draw a line from 0, 0, the origin, to kind of the middle of the screen. And then anything specified after, this is your starting position and this is your ending position in XY coordinates. Anything specified after this is just forwarded along to your pixel drawing function, so the display.pixel function. So this is where you specify your color basically. And if you're drawing on something that requires, that you specify an 18-bit color or whatever, just send it along as an extra parameter here, and it will get passed along to that pixel drawing function. If you have multiple parameters, like maybe your pixel drawing function takes in like a red, green, blue, explicit values, all of those will be forwarded along too. So just put whatever color data you need, or maybe there's not even color, maybe it's just intensity or an on-off or true-false or something like that. The nice thing is this graphics library doesn't care. It's just going to take whatever you send it, and through the magic of Python, and if you're curious, the way this works, every function in Python can have these special parameters. If you have a star and a star parameter, the star parameter basically says, grab any extra positional arguments. And so these things right here are basically positional arguments because they have to be specified in this order. So if someone called your function and added extra positional arguments, and you had one of these star args parameters, it will actually be set as a list with all of those extra positional parameters. And same thing for this KW args and star. This is just for keyword arguments. And so keyword arguments in Python look like at the very top, like these parameters right here, where I have like hline equals none. This is telling me that, okay, you can specify an optional hline keyword parameter in this initializer. And so that means I have to specify this. I think you can specify it positionally, but in most cases you say hline equals some function or whatever when you're calling this initializer. So there is a difference in Python between those keyword and positional arguments. But this is how you can basically say, with the star args and star KW args or keyword arguments, you can have a function that takes any number of parameters, either keyword, positional, doesn't matter. They'll all get sucked up and thrown into one of these two values right here. And then I can actually later on take these, and when I call my pixel function, I can tell it, okay, call this pixel function and pass in an x and a y position right here, and then take that args parameter, which is a list, and unpack it. That's what this star in front of here means. Take each of those list entries and just map it directly to all of the positional arguments in this pixel function. And the exact same thing for the keyword arguments, whereas the keyword arguments are actually given to you as a dictionary that have, for each of the keywords as the name, and then the value is set to whatever that parameter value was that was passed in. But again, this star just says unpack that dictionary and pass it to all the keyword arguments of this function. And so that's kind of how that forwarding works. And that's why, right here I'm passing in this color value, and that will just get passed to my pixel function using that args and keyword arguments parameter. So a very handy thing that Python has that lets you do really nice code like this that's kind of dynamic. It doesn't care how many arguments you have. It's just going to pass them all along and ignore them, because when I'm drawing the line, I don't care what color it is. It's only the pixel function that cares what color it is. Okay, a lot of talking. Let's actually run this thing. And so we should see a line that's going to be drawn. So I'm going to use ampy to run, and it's in the examples folder, this ILI9341 test. So I'm going to run this, and hey, look at that. You can see that the line was just drawn like that. And so let's change this. Let's make it draw across the entire display. So we'll go from 00 to 239 and 319. So this should draw across the whole display. Now watch as it draws. You can actually see, you're kind of watching it draw pixel by pixel. So, boom, there we go. So that took like maybe 2 seconds or so to draw across the entire display. So that's kind of showing you the speed of this is not the fastest thing in the world, because if you look at the code for this, that line drawing function is right here. And so this is all in Python that it's doing this. And again, like I mentioned, it's using this Bressenham's algorithm, which kind of looks at what's your rate of change, and then it adds your rate of change every step, and then it calculates the error, and at some point when the error is high enough, it moves to the next row. So all of that logic is implemented here in Python code, which has to be interpreted and run with MicroPython. So that's why you see that update. I mean, some of that is just the speed of pushing pixels over the SPI bus, but again, we're running at 32 megahertz, and so pushing a single pixel at 32 megahertz, that should be pretty fast. But calculating all those positions doesn't happen for free. So this is maybe a case where, if you're doing simple updates, like if I was writing a line on this little 5x8 NeoPixel grid, there aren't a lot, there are 40 pixels total, so that's not a lot of pixels. Drawing a line across this thing should be really fast, even in MicroPython, because you're not going to draw more than, 40 pixels or so of a line across that thing. So, that's a case where maybe the speed doesn't matter. You're just drawing things to pixels, your lines are only going to be a few pixels long, who cares? Whereas when you have this 320 by 240 size display, okay, now you've got a lot of data to push, and so maybe the Python implementation isn't fast enough. So in the future, we might look at like a C implementation of this, where this code is in C and maybe draws against a frame buffer in memory that you can then blast out to this display really quickly. But maybe if you're doing something slow, if you're just drawing like, here's the current temperature sensor state, like draw like a red circle if it's high and, a green circle if it's good and okay. Who cares how fast it draws? And speaking of circle drawing, so let's test out some of the other examples here. So you can draw a line, obviously. You can draw a filled circle, or even let's just start with a normal circle. So this is going to draw a circle at the origin, or not the origin, but at the middle of the display. So position 120, 160. This is the radius in pixels. So this will, let's make this higher. Let's make this 50 pixels wide. And then the color, this is a pink color that it's going to use. So let's run our example this time. And so now you can see it just drew, there is a perfect circle right in the middle there, a pink circle. It was kind of neat though, you can see how it draws this. And so it draws like from each quadrant kind of forward. And if you're curious, you can look at the code for this once this library is published. Again, this is something that Phil B created, and you can actually see how this works. So it starts out by drawing, it draws basically all the extremes, like the top, the bottom, the left, the right pixel. That's what these four are. And then it goes through and it just kind of draws each of these quadrants, it just draws out. So there are kind of four quadrants to this circle. And so that's kind of what's happening right here, is each loop iteration, it draws more of the pixels inside of that quadrant there. So that works. You can also do a filled circle, so fill underscore circle. Now, this is a case where you're going to see it's a little bit slow. So let's run this. And now you can see it's drawing basically horizontal line by horizontal line across the display, and this is not very fast. Now this is a case where filling in that vertical line function, that V line function that I mentioned up here, if I had a faster way to draw a vertical line, and there might be one, I haven't really looked at the ILI display, but if there's a fast way to do this without drawing pixel by pixel, that could speed this up, because the way this circle drawing is implemented is it's just drawing vertical lines for each of the slices in that circle. So there you see it finished. That took like 10 seconds or so. So not the fastest thing in the world for that, but it does work. It's, and again, this is cool because you can use this on the Charlieplex display. You can use this on the LED matrix. You can use this on a NeoPixel grid. Doesn't matter. As long as you can draw a pixel, you can draw circles, you can draw lines. Okay, and then oops, I just deleted that on accident. Okay, the next thing I'll show, let's just skip to the triangle. I already showed you kind of rectangle drawing. Well, okay, what the heck, we'll show rectangle drawing for this. Instead of a filled rectangle, we'll just do an empty rectangle. So this is going to go from position 0, 0 to the middle with a red rectangle. So I'll run this, and you'll actually see this one, again, is kind of slow. So you can see this works by drawing horizontal and vertical lines. So if you had faster versions of those, it would be a little bit faster, but this is still kind of, a little bit slow. It's kind of the unoptimized versions. And there's a filled rectangle version of this that you can use. Okay, so there is also a triangle function, and let's start with the non-filled version. So this takes 3 points, and maybe I'll make it a little more clear. So there's 0.1, 0, 0, 0.2, which is kind of a little bit below the origin or the middle of the screen, and then a third point, which is over here on the left here. So let's save this and let's run it, and you'll see that, hey, look at that, it's drawing a triangle. So you have kind of a right hang, what is the name of that triangle when you have a right angle there? Well, it's one of those triangles with a right angle on it. I should remember that. This is like 7th grade math, but the simple little triangle. Now it's actually a little bit lower here, and I'll show you. So if I switch this to the fill underscore triangle, this will work. This is going to be really slow, and you'll actually see the speed of and how this thing renders. So you can see it's drawing kind of horizontal line by horizontal line each of the lines in this rectangle. or in this triangle. So it's going to go through and eventually it's going to finish rendering this thing. But the reason that I didn't do a perfect 90-degree triangle is that there's actually a small bug in the code right now, and this might actually be a bug in the Arduino library because I ported it over directly, but it's kind of interesting in that in MicroPython it behaves a little bit differently. So here's the fill triangle function. It's basically just figuring out like what are each of the horizontal lines that I need to draw to make this triangle, and it's a little complex here, but it does some division, and this divide is actually integer division in Python 3 specifically. So you do need to be explicit, because if I just did a single divide, it would do floating point division, which this code is not written to expect floating point division. It's actually using integer types in C, which would never have a floating point value. So that is a big difference when you're porting code from C to Python. If you have int types, make sure to do integer division, or else you'll get wacky results that you might not expect. But there is a division happening here, and there's actually a case I noticed right here where this dy12, this is your delta between your second and third points in your x dimension. This might be 0. And so if you're x2 and x1, if your last 2 points are on the same horizontal line, then your dx12 value is 0. Right here, you're going to try to divide by 0. And let's see what happens when you try to do that. So let's set this to, this is a case where here's my second point, its y position is 160, and my third point, its y position is also 160. So they're on the same line. So that dx12 is going to be equal to 0. And so when I run this one again, we'll see it's going to start to draw the whole thing. But then once we get to that last line, we'll see something interesting happen here. So I think that this actually might be a bug in the Arduino library too, but we probably never notice it because on Arduino and C, it's kind of undefined behavior when you divide by 0. So it might do nothing. It might just ignore, you might get a 0 value back. It might crash the processor. So you don't really know what's going to happen. In Python, we'll see what happens in a second here when it gets down to that line. So we're almost there, and uh-oh, we just got an error. So this is nice in that Python tells me I got a 0 division error. So Ampy basically ran this script, and then the script failed. It threw an exception, and Ampy is giving me back the exception here. Not the best kind of format, but right now you can basically read this exception and see 0 division error. It's telling me the line also, line 198 in the fill triangle function. So if I go to line 198, you can actually see that, interesting. Why is it giving me the error here? Not sure why. It's maybe because I changed this GFX library. Oh, I added more comments to this, so the line numbers are off a little bit. But ultimately, this is where it's failing, because dy12 is equal to 0 in this case. And right here, I'm trying to divide by 0, so I'm getting that division by 0 error. So I need to think through what this module really means to do when you get that case. I think what I need to do is add a special case, maybe even down here where if dy12 equals 0, then I just probably have to assume that a equals x1. Like there's probably nothing that this SA adds to it, so I need to go through and kind of understand how this algorithm works. But I'm guessing that this is a special case because this only happens when your two last points are on the same line, same row. And I'm pretty sure that there are other cases where this would happen. Like, for example, you can see, I'm dividing by dy02. And so dy02 up here, okay, if my third and first point are on the same line, then I'm going to get the exact same divide by 0 error right here. So interesting little thing that I noticed here as I ported this to MicroPython, that, Python is a little more explicit, and instead of doing undefined behavior, it throws an error when it realizes you're trying to divide by 0, because mathematically that means nothing. And so you need to kind of think through, okay, what does that mean to my algorithm when a divide by 0 happens? I mean, in some cases, that's maybe like a weird edge case, and I should just ignore that and do nothing. In other cases, maybe it makes me realize, like, oh no, this is broken. Like, I actually have to handle something differently here. So that's kind of the fun of doing, converting code from C to Python here. And like I said, this is the GFX library. It's not mentioned in the guide yet, but look in the future, in the next day or two, I'll probably have a new module and a new guide that shows how to use this library. And I think this library is going to be useful for like pixel displays that are low density, like, these little NeoPixel grids, high density displays like this that have, hundreds of thousands of pixels. you're probably going to be a little too slow to use this library. But in the future, we'll probably have a C version of this that'll be faster to use these displays. So, okay, that's it. I'm going to wrap up this stream then. If folks have questions, throw them into the chat, and we'll go back to kind of the main headshot here for this. You can see the cat's in the background here. She's been the faithful companion along the way. She's just sleeping right now, so nothing too crazy going on. Okay, let's see. Yeah, I don't see too much question-wise. Okay, question, will this hang the right way if you put it in a doubler? Will it overhang the other slot in the doubler? So yeah, good question. I have a doubler right here, but it is glued to my robot. Oh, here, you can't see the, well, here, let's jump back to the workbench shot, and let's see what we have here. Okay, so I think the question here was, can you use a FeatherWing doubler with this thing? I don't know. So I have a doubler right here, but I actually taped it to my robot here. So all right, let's pull this off if I can. Okay, yeah, there we go. The tape's coming off. All right, let's see if we can use this thing. So let me pull the double-sided tape off the back of this doubler. Okay, there we go. So here's the FeatherWing doubler, and I have, this is the motor driver connected to it right now from the old robot project. Okay, so the way this thing works is you can put one feather on here and another like FeatherWing on here, and these are just electrically connected. So I don't know. Let me close. Let's pull this chip off. So your first problem obviously is that these are female headers on this board, and your doubler, if you wired it up to connect to FeatherWings, probably has female headers on it like this. So you're going to need probably a row of male headers plugged into here. The interesting thing is the orientation though. So, you know, this would probably work if you took your doubler and instead of soldering female headers onto it, if you solder male headers right here onto this, then you could plug it in like this, and you'd have an extra row right here where you could probably put like female headers and then plug in a FeatherWing. You could actually, you could put the stacking female headers on here, which are like a longer header meant to stack across different FeatherWings. Like, for example, let's see, I think I have one here somewhere. Yeah, here we go. So on this board, let me pull this one off without yanking all the pins off. Come on, here we go, almost out. There we go. So these headers right here, these are the stacking headers for feathers. So you can see that this is basically on one side a female header, and then on the other side they're nice long male headers. So this can plug in, and then you can stack other things on top of this. If you put these headers onto your feather doubler like this, then you could stack the feather doubler onto here, have something on here, have another one on here. You could even stack it probably like this, it looks like. You know, if you use these long headers, because this will stick a little bit up, then yeah, this should fit over the top like that. So I don't see any reason why it wouldn't work like this. So, you know, worth giving it a shot to see if you can use both of those for that. So okay, let's see if there were other questions. We'll jump back to the main headshot view here. I think this is it. So yeah, I think that was it. No other questions. So okay, cool. So thanks for watching. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos there. Check out twitch.tv/Adafruit. You can watch me stream these things live. I like to do at least a couple streams per week. I try to do one on Tuesdays. This week was a little bit of a busier week, so I couldn't get a stream until now. But look forward to Tuesdays usually, and then Fridays I like to do another stream. And so hopefully tomorrow I'll do a stream on that graphics library that I was starting to kind of hint at in this stream. And you know, look forward to a video and a guide on that in the future. And then programming note, I think next week I won't do any streams because it's Thanksgiving holiday week, and so there's a lot of things going on. Good week to just kind of spend some time to do some other cleanup and stuff like that. So probably no videos next week. Enjoy the holidays, and then we'll be back with at least a few more weeks of streams before kind of Christmas and some of the other holidays that are coming up. So check out youtube.com and twitch.tv/Adafruit. Watch all the fun videos. Click the like, the comment, the subscribe. You know, let us know that these are cool videos and that you're getting good info from them, and we'll keep making them. We'll keep doing all kinds of fun MicroPython content. So until next time, this is Tony from Adafruit. I'll see you later. Thanks.